All right, 11.2. We got areas of trapezoid, rhombuses, and kites. Let's take our first one. This is the formula associated with the trapezoid. 1/2 times the height, base 1 plus base 2, which we explored in class. Remember, these are parallel. Go ahead and draw this down and put it in your notes. Let's go ahead and use it. The free throw lane on an international basketball court is shaped like a trapezoid, as you see in this picture. Go ahead and draw the picture down, and let's find the area of the free throw lane. Free throw lane being what we would call the paint in basketball. Let's go ahead and erase that. All you have to do is identify what you need for the formula. Remember, the formula is 1/2 times the height, base 1 plus base 2. Once you get all your values, you just plug them in. So the height between these two bases is 5.8. 5.8, and we're going to multiply this by base 1, which I'm going to call the bottom, plus the top one, be base 2, and then we multiply this by 1/2. Then we just need to make sure we get a calculator, and I've got mine right here, and we plug it in. If you don't have a calculator, obviously you have to do this with the good old arithmetic. 5.8 divided by 2 times 6 plus 3.6. I get 27.84. Now we're looking for the units here. Notice the units are in meters, so this is meters squared. Checking my work, 5.8 divided by 2. Yep, looks good. Next concept is a rhombus. Remember, a rhombus has 4 congruent sides. We'll prove this in class, but note that the area is simply the 1/2 times diagonal 1 times diagonal 2, remembering that diagonals bisect each other in a parallelogram. In this case, it's a rhombus. So the diagonals do bisect each other. All right, let's solve this problem. Go ahead and put this, by the way, put this one back in your notes. Let's go ahead and put this one in our notes. You don't have to really draw the guitar, but let's go ahead and draw the inlay and solve for the area of the inlay. And inlay is the part of the, sorry for the bell. Inlay is the part of the guitar. Notice we have 9 for here, remembering that this bisects with this, so this is 9. That means that diagonal, we'll call this diagonal 1, is 18 millimeters. Diagonal 2, well, this also has to be 12 millimeters, so diagonal 2 is equal to 24. Plug this into the formula. We have 18 times 24 divided by 2. And I get 216 millimeters squared. Booyah! Next one, this is a kite. Remember, kites have 2 pairs of congruent adjacent sides. Notice these are adjacent and those are adjacent. It's the same formula, which is kind of crazy. Just a quick thought for both of these. Notice there is a triangle and there's another triangle. So it's just the area of both the triangles added up. We'll talk about that more in class. Go ahead and draw this in your notes, please. Let's go to the next one. Write this problem down in your notes because we're going to need to be able to solve it. Notice we have variables in this case. It says one diagonal of a kite is twice as long as the other diagonal. So that means that there is some part x that both of these diagonals share. And it says the area of the kite is 90.25. Well, the area of kites is one diagonal times the other diagonal divided by 2. Let's go ahead and simplify this while we're at it. Notice 2 divided by 2 cancels. We're left with x squared. And this is equal to the area, 90.25. That means that x is equal to the square root of 90.25. And there's a little bleed there. So square root of 90 point, if I could type, I get 9.5 as the x value. What are the lengths of the diagonals? Well, x is one of the diagonals, and the other diagonal is twice that. So twice that would be 19. So I'm looking for 9.5 and 19. That would be C. All right, you have a map of a city park. All I really want to have in your notes is the drawing. You just have to draw a quick sketch of it, write your trapezoid out. Notice this trapezoid lands at nice, pretty values. Let's read the rest of the question to make sure we're understanding. Each grid square represents a 10 meter. They also labeled it on the graph. And find the area of the park. The area of the park, well then, we just need to count this base and the other base and the height. Because remember, our formula is 1/2 times the height times base 1 plus base 2. Base 1 is 1, 2, 3, 4, 5, 6, 7. 7 times 10 is 70. And this is 1, 2, 3, 4, which is 40. The height is 1, 2, 3, 4, 5. 5 divided by 2. Then it just comes down to chugging this out. 70 plus 40, multiply that by 5 divided by 2. Oop, 50 divided by 2. And I get 2750. Checking over my work, 70 plus 40 times 50 divided by 2, and this is meters squared. All right. Go ahead and pause the video, try this out. I'm going to show the answer here in just a second. Is that what you got? All right, moving on. Area of a kite is 80 square feet. So we have area. Diagonal is 4 times as long as the other. Go ahead and write this problem down in your notes. We have area. Remember that the area of a kite is diagonal 1 times diagonal 2 divided by 2. Let's find the diagonals. It says 4 times as long as the other. So we have some diagonal that's x, and the other one has to be 4 times x. So let's set up our equation. We have x times 4x divided by 2, and this is equal to 80 square feet. So notice the 4 divided by the 2 becomes 2, and x times x is x squared. Oops, working ahead in my head. Shouldn't just yet. 80 divided by 2 is 40. 40 is equal to x squared. Note that we have x equal to plus or minus the square root of 40. But talking about this being geometry and side lengths, we only allow the positive value. So I'm going to cancel out that negative. This becomes positive square root of 40, which becomes positive square root of 4 times the square root of 10, which becomes 2 root 10. And if you need to use this to answer a distance, it's also necessary for you to plug it in, turn into a decimal. So we have x approximately equal to 6.32. Let's read our question to make sure we've answered it. It says find the diagonal lengths. This isn't applying to some figure or anything, and it's in feet. All right, I think we have one more. Another bell, sorry about that. Find the area of the rhombus with these vertices. Go ahead and sketch out a quick graph, plot those points, try this problem, pause the video and see if you get the same thing as me. Is that what you get? All right, just a few thoughts here. Yeah, it would be a little bit tedious to find that distance using the distance formula, but we're finding the area of a rhombus, and that is diagonal 1 times diagonal 2. Notice this is set up nice and conveniently for us because this diagonal is horizontal and this diagonal is vertical. So I just count those values. That's where I got the 4 and the 8, and then I plug it in to the formula and simplify. I believe that's it.